This video presents our work called PlaceNav, Topological Navigation through Place Recognition. Learning robot navigation from offline demonstrations has received increasing attention in the recent years. General Navigation Model by Drew Shah et al. Is a seminal work on the topic. Here, the aim is an embodiment-agnostic foundation model that can be used for navigation with different robot platforms. This is made possible by training on offline navigation datasets collected with various robots. GNM achieves impressive navigation performance in real-life scenarios. However, we noticed that in GNM there is a module that isn't tied to robotics at all, with potential for even more generalization. GNM and the previous works formulate navigation as a sequence of image goal tasks, also known as topological navigation. Choosing which sub-goal image to try to reach at any given time is an essential part of the topological navigation pipeline. The realization that started this work is that sub-goal selection can actually be viewed as a place recognition problem. Place recognition means recognizing a scene across different viewpoints and across appearance changes. Place recognition has been extensively studied in the computer vision community for many years. This made us curious to see how well the GNM sub-goal selection performs in a standard place recognition benchmark. And you can see the results for that evaluation here. We were a bit surprised to find that despite GNM's strong navigation performance, a model trained with the place recognition methodology outperforms it by a wide margin. The method that GNM and the previous works utilize for sub-goal selection is called temporal distance prediction. As demonstrated by GNM, temporal distance prediction models are powerful enough to enable real-world navigation. However, they have to be trained on robot navigation datasets, which are relatively scarce, and they also have a high runtime computational cost, especially for larger map sizes. Inspired by the results of the VPR benchmark evaluation, we decided to replace the GNM sub-goal selection module with a place recognition model. Place recognition has the advantage that there exist large-scale datasets for training the models. Also, place recognition inference speed is very fast compared to temporal distance prediction, as much of the necessary work can be performed offline prior to robot operation. To mitigate some of the issues related to long runtime of temporal distance prediction, previous works utilize a sliding window filter on top of the temporal distance model. The idea is to limit the number of sub-goal candidates per time step based on the previously chosen sub-goal. This increases the temporal consistency between consecutive sub-goals and helps reduce the runtime of sub-goal selection. Sliding window is a useful heuristic, but suffers from problems such as getting lost. The fast inference speed of place recognition, however, enables the use of more advanced temporal filters. To test our place recognition-based system, which we call PlaceNav, we conducted navigation experiments with 2 real robots in both indoor and outdoor environments. We compared sub-goal selection by place recognition to a temporal distance-based method from the GNM. We report the success rate, which is the percentage of trajectories completed without getting lost or colliding with obstacles. And you can see that PlaceNav improves upon GNM by 10 percentage points. The difference was even higher in difficult cases. Enabled by the fast inference of place recognition, we also implemented a more advanced temporal filter in place of the sliding window filter. Our Bayesian temporal filter further increases the success rate by 11 percentage points. Here you see the runtime durations per step for the different methods. With all map sizes, the place recognition-based methods are significantly faster than the temporal distance-based ones. Furthermore, the place recognition inference speed does not depend on map size. As contributions, we present a faster and more accurate approach to subgoal selection for topological navigation, and as a more general takeaway, we argue that by dividing an application to very generalized modules, the amount of training data per module increases, and so does the performance in the downstream tasks. Thank you for watching the video. If you're interested, please check out the website for more videos, the code, and the article. Thank you.